Okay, this is worksheet 1216 part 2, which is the 2019 FRQs. Really good practice for your AP test this year. You should have tried these on your own and then see how well you can do. And then watch this video and figure out some of the easy stuff you missed and some of the harder stuff and how to do it. So, a cylindrical barrel with a diameter of 2 feet contains collected rainwater as shown in the figure above. I put it down here. The water drains out through a valve not shown out the bottom of the barrel. The rate of change of the height h of the water in the barrel with respect to time t is modeled by dHdt negative 1/10 square root of h. So they give me a dHdt, and then they give the volume of the cylinder, which should be easy. So, I mean, my first instincts are this kind of feels like related rates. Like, might have related rates in it. Probably not the whole thing, but it could be a rate model problem because we have things changing. It says A, find the rate of change of the volume of the water in the barrel with respect to time when the height of the water is 4 feet. Indicate units and measures. Definitely always put units. So we're looking for, I'm just trying to summarize what we have and what we're looking for. We're looking for the rate change of the volume of the water in the barrel with respect to time. It says when h equals 4 feet. And we also know that dH dt equals negative 1/10 square root of h. Now, I think it's uncommon that they give you the negative on the rate of change of the height. They would say something like the height is decreasing, or the water's coming out of the barrel, so you would know it should be negative. But that's fine. They gave it to us. So I think this is the related rates part of the problem because we have volume equals pi r squared h. Now, the radius of the barrel is always 1 foot, so it would be very helpful to plug that in right now for the radius, so that when we take our derivative, it doesn't have to be this ugly product rule. Okay, so that's going to save you some pain. So we're going to take the derivative. dv dt equals pi dH dt, right? And dH dt is negative 1/10 square root of h. So we get negative pi over 10 square root of h is dv dt. We want dv dt when the height is 4. So we're going to plug 4 in for height, and then we're going to get negative 2 pi over 10, which is negative pi over 5. The units are volume cubed, feet cubed, over time, which is seconds on this problem. Look back up. And so that's your dv dt. Okay, now the point breakdown on this problem is 2, 3, and 4. So you got 1 point for doing the implicit derivative, and then you got 1 point for your answer. And you have to have units in it, otherwise you lose the question. Part B says when the height of the water is 3 feet, so h equals 3, is the rate of change of the height of the water, so that's dH dt, with respect to time, increasing or decreasing. Now you got to be careful here. And this came up on another problem, I think. The asking is the rate of change of the height increasing or decreasing. They're not saying is the height increasing or decreasing, because that would be dH dt positive or negative, but they're saying is this increasing or decreasing. So we have to take the derivative of dH dt. So I'm just going to write down what dH dt is real quick, which they gave us. I think it would be too easy if they just said, is the height increasing or decreasing, because you just plug h in and be done. But definitely would only be worth like 1 point if that were the case. But we have to take the derivative of h. So we're essentially getting the second derivative of h. And this is negative 1/10 h to the 1/2. So this is going to be negative 1/20 h to the negative 1/2 dh dt, right? And that's worth 2 of your points there. Pulling that off. Now I'm going to rewrite it now. DHCT, I can plug in what we already had. And it was negative 1/10 square root of h. And then it really simplifies down nicely. It gives you positive 1 over 200, which is always positive. So it doesn't even matter that h is 3. We don't even use h is 3. It's always increasing. So I'm going to write that down in words. I'm going to say the rate of change of the height of the water is increasing when h equals 3 feet, since the derivative of the rate of change of the height equals 1 over 200, which is always positive. So it seems like a good. Now, so your last point was for your answer with explanation, justification. Okay. Part C says 4 points. That's a lot of points. It says t equals 0. The height of the water is 5 feet. So they're saying h0 is 5 feet. It says use separation of variables to find an expression for h in terms of t. You're trying to solve for h. Now, I know this doesn't seem like the typical differential equation, but it's a differential equation. We're trying to solve the differential equation. And I would say that's more common in recent years, is it's not so obvious. Like, oh, this is a differential equation problem right from the beginning, like slope field and all that stuff. It's buried in this problem, but really, this is just basic solving a differential equation. So you got to separate the variables. And that's a point. Okay. We need to integrate both sides. Now I'm going to rewrite this one as h to the negative 1/2. And so it's going to be, you're going to bump it up 1 and divide by the new exponent. This is going to be negative 1/10 t plus c. So you got 1 point for the antiderivatives. Now the plus c is usually a point, and then finding plus c is a point, but the plus c and finding plus c all together is your 1 point. So now we need to use the initial condition that they gave us. And so then c equals 2 root 5. So find the plus c and finding the plus c using initial condition, that's worth a point. So then we're going to plug it back in. 2 square root of h equals negative 1/10 t plus 2 square root of 5. And then we're going to solve for h. So square root of h equals negative 1/20 t plus root 5. Then we're going to square both sides. So h equals parentheses negative 1/20 t plus square root of 5 squared. Now, of course, we always need to worry about domain. So the domain, we got to worry about some different things. We look here, we say, well, are there any values of t that would cause problems? Even roots of negatives, division by 0, natural logs of negatives of 0, so forth. No, but there is a problem up here. The derivative has to be defined, and h has to be greater than or equal to 0. H is what we just found, negative 1/20 t plus square root of 5, greater than or equal to 0. So we're just going to set it equal to 0. So that's going to be 1/20 t equals square root of 5. T equals 20 square root 5. And so this is an issue in our domain. The other issue in our domain, because our domain is time, this is a real world problem, and we're not going to have negative time, right? I don't think they said anything about that, but I think you should assume that this starts at t equals 0. So your domain is going to be, now generally, any discontinuity or indifferentiable spot is an open dot because it's going to be a single open interval, but time 0 isn't because of a discontinuity or an indifferential spot. It's just a restriction on the problem. And then we want to include the portion of the graph. So, technically the domain would go all the way to negative infinity unless we had this real world restriction that we should stop at that. Now, the other way to make sense of this is that the height of the water in the cylinder can't be negative. You can't have negative water in the cylinder. I mean, just calculus wise, it gave us this answer, but this is also the time when the water in the cylinder is 0. And the water can't keep draining if there's no more water. So that's your domain. Okay. So we got a point for separating the variables. You got a point for the antiderivatives. You got a point for plus c and finding c, and then you got a point for your final answer and domain. So that was a differential equation, kind of hidden a little bit, not so obvious as normal. So number 5, right away, kind of looks like maybe an area volume problem. The fact that they're giving you a picture of it. It says, let R be the region enclosed by the graphs gx equals this and hx. Now, we don't have a calculator. Now, can you figure out which graph is which? One of these is an upside down parabola, and one of these is a cosine curve. So this one looks more like the cosine curve right here. So you can double check. If you plug 0 in, you get cosine 0 is 1 times 3 is 3 plus negative 2 is 1, which makes sense. So you could also check just by plugging in some easy values to see which graph it is. So this is for sure the cosine curve. It looks like a cosine curve. This is going to be our upside down parabola. And so I like to label these on the graph. Graph would usually be above. I just put it down here to fit it better on here. It says the y-axis, a vertical line, x equals 2. So there's that line right there, x equals 2. These graphs keep going. Okay, so we have all these corners that we might need. So this is 0, 1, and this is 0, 4. You could double check. If you plug 0 in here, you get 6 minus 2 is 4. This is 2, comma. If you plug 2 in here, you get 6 minus 2 is 4. If you plug 2 into this graph, you get cosine of pi is negative 1, negative 3, negative 2, negative 5. So that kind of matches up right here, right? Okay, so I just kind of figured all that stuff out. Now, part A says find the area. All right, probably going to do vertical slicing. I think that's the most convenient. So we're going to find the area of region R. And so we're going to integrate left to right, 0 to 2 in the x direction, top curve minus bottom curve. So it's going to be hx minus gx dx. Now, if we had a calculator, we could just leave it like this and then plug in a calculator. By the way, that's a point. But since we're going to have to integrate it by hand, we're going to go ahead and write these functions in here. So this is 6 minus 2x minus 1 squared, and then minus this one, negative 2 plus 3 cosine of pi over 2x. Now, I'm being careful here and putting extra parentheses to separate this subtraction of all of this because we have to distribute that. So we have a little bit of tedious work cut out for us right now. We could try and just integrate each of these on their own. Antiderivative 6 is 6x minus 2. This is going to be x minus 1 to the third power divided by 3, 0 to 2, minus, this is going to be negative 2x plus this is going to be sine of pi over 2x positive, and then an extra pi over 2 is going to pop out that I don't want. So I already have a 3, but then I need an extra 2 over pi. You could do u substitution to show that. Now we get another 2 points for the antiderivatives. Okay, so point for the antiderivatives. So just you getting points for knowing how to integrate correctly. Be careful. And then we're going to plug the values in now. When I plug 2 in here, I'm going to get 12 minus 2/3. And plug 2 in here, it's going to be 1 cubed is 1. And then if you plug 0 in, it's going to be 0 minus, now this isn't 0, it's going to be negative 1/3, which is negative 1 times negative 2 is plus, so it's going to be plus 2/3. Right? So that's the first one. And then the next one is if you plug 2 in here, you get negative 4 plus 6 over pi. Sine of pi is 0, so that goes away. Minus, if you plug 0 in, you get 0 plus 6 over pi. Sine of 0 is 0 again. So all those terms drop out. We do have a negative 4 there. Okay, so the answer is going to be 12 minus 4/3 plus 4. And so we could write that as 16 minus 1 1/3. So it'd be 14 2/3, or 3 times that would be 44/3. So your final answer is a point. But that was the point breakdown here is going to be 4, 2, and 3. So we've got a point for setting up, got a point for each antiderivative, and then a last point for the answer. Part B says region R is the base of a solid. For the solid at each cross section perpendicular to the x-axis, the area is this formula. Now, usually this is volume by cross section, and usually they tell you the shape, and then you have to figure out what the area formula is, the geometric area formula. But here they're not telling you the shape; it's some weird shape, but every slice has that area. So this is actually a little easier than normal because we're going to integrate left to right 0 to 2 of some area x. This is what I usually write first, and then I draw a shape, and then I figure out what the shape is. But they already did all that for you. They said this is the area formula in terms of x. So I can see that messing some people up, but that's actually less work than normal. So now we have to integrate this natural log, the absolute value of x plus 3, 0 to 2. We plug 2 in to get natural log of 5, plug 0 in to get natural log of 3, and that's fine for an answer, or you could use log rules to combine these together, which you probably have to do on multiple choice. And so that's a point. So 1 point just for setting it up, just writing AX, that's a point. So that was kind of weird, volume by cross-section problem, without telling you the area, the type of shape the slices are. And they just straight out give you the area. C, write but do not evaluate integral expression that gives you the volume of the solid generated when R is rotated around the horizontal line y equals 6. Now my graph up here is really busy and I don't have much room, so I'm going to go and just redraw this. And it's going to be around y equals 6, which is up here. So we definitely need more room above. And so I'm just going to try and recreate this. So 1, 2, 3, 4, 5, and 1. So this is the first curve. Okay. And then 1, 2, 3, 4. And then so the next curve is like that. And then it actually goes up to 6. So it's kind of like this. So, I mean, this is taking a little bit of time, but I feel like it'll pay off. I'll get the problem right. So then it's being revolved around y equals 6, right? So then I'm going to draw this version up here just to kind of get something. So this is going to be 2, 3, 4, 5 away. 6, 7, 8, 9, 10. Is that right? I don't know. Anyways, it doesn't have to be perfect, but something like that. Okay. Good enough. Okay. So we're going to do, I'm going to, stick with the vertical slicing. I don't think we really want to deal with shells and horizontal slicing when the two curves here. So it's going to be dishwasher method, which is really all they usually expect of you. So it's going to be pi big R squared dx minus pi little r squared dx. Integrate. We're going left to right, 0 to 2, 0 to 2. So all we need to do, because we're not even going to finish this, is we got to figure out the big radius, which is always down here on the original region. This one up here is just to help us. And the big radius is y top minus y bottom. The little radius is also y top minus y bottom. And so for the big radius, y top is 6, and y bottom is the y coordinate along the cosine curve. So parentheses, -2 plus 3 cosine of pi over 2x. Close that, square dx minus pi 0 to 2. Little radius is also y top is 6. Y bottom is the y coordinate of that curve, the upside down parabola, parentheses 6 minus 2, parentheses x minus 1, squared, close, squared, dx. Be very careful here. There's a lot of parentheses and things like that. So you get 1 point for the limits and the constant, and then you get probably, I guess, 1 point for each. Now, you know what I should have done, because we weren't going to actually solve this, is I should have just used the names, because this was gx and this was hx. So here, just starting over again real quick, but a lot easier, it'd be pi 0 to 2 of 6 minus gx squared dx minus pi 0 to 2 of 6 minus hx squared. So that would have given you the same full credit, but a little more convenient to write without having to worry about all those extra parentheses. So there you go, a little area volume problem. Let's see, number 6. So let's take a look at this. Functions f, g, and h are twice differentiable functions. Okay, might need that for something. They give you some initial conditions for g and h. They give you a tangent line. It's tangent to both g and h at the same point. So graphs g and h, we don't really know what they look like, but they both, I guess, touch each other at x equals 2, and they both have the same tangent line. So let's see, find h prime of 2. So, well, let's see. We don't have function h, but we do know the tangent line there, right? So the slope of the tangent line will be the slope of our graph. So the tangent line is y equals 4 plus 2/3 x minus 2. And that's the slope of the tangent line, right? So this h prime 2 equals the slope of the tangent line. I'm just trying to explain my thought process, because, tangent line to hx at x equals 2. And so that is going to be 2/3. But that was pretty easy. Now, point breakdown here is 1, 3, 4, 1. So no surprise, that was 1 point. Okay? Part B says, let a be a new function. Oh my gosh, there's so many functions here. A equals 3x cubed hx. And it says, write expressions for a prime x and then find a prime 2. Okay, so a prime x It looks like we got to do like a little product rule there, right? So it's going to be 3x cubed times the derivative of h, which we're just going to write h prime x, plus hx times the derivative of 3x cubed is going to be 9x squared. So that's a point right there. You did the product rule, and I think you can get the right answer as a point. And then we're going to do a prime 2. So we're going to plug 2 into all this. So 3 times 2 cubed, h prime 2 plus h of 2 times 9 times 2 squared. So that's going to equal 3 times 8 is 24. Now h prime of 2 is what we just found. Part A, it's 2/3, right? Plus h of 2, they gave you at the beginning was 4 times 36. So that's going to be 16 plus 120, 144. So a prime 2 equals 160. So that's a point. So there we go. Not bad. 3 points. C, H. So they've talked about H, but it says H satisfies HX equals x squared minus 4 over 1 minus parentheses f of x cubed for x cannot be 2. Okay, so they actually gave you the value of h2. They said it's 4, but when h equals 2, like maybe this is undefined or something. And so they say that it doesn't work there. Now it says, it is known that the limit as x approaches 2 equals h of x can be evaluated using L'Hopital's rule. Use the limit as x approaches 2 of h of x to find f of 2 and f prime of 2. Show the work that leads to your answers. Okay, so this is kind of interesting. They're not asking you, you're not being asked to use L'Hopital's rule or realize that you should use it. They're telling you it works. Okay, so whatever needs to be true to use L'Hopital's rule, they're saying you can use. So I'm probably going to start with that and just start looking at this. Like if we were to take, it says that they want you to find the limit as x approaches 2 of h of x. Well, let's just write that down. Let's see what happens. And so if you plug 2 in, or hold on, I'm going to just write down its original form first. Okay, so if we plug 2 in, we get 2 squared minus 4, which gives you a 0 on top. On the bottom, we get 1 minus f of 2 cubed. Now, they said we could do L'Hopital's rule, which means that the bottom of this has to be 0 too. And that's going to give you, and we know, I don't know. So let's see. So from that, we're going to be able to find f of 2. Okay. It says it is known. Okay. So we're not trying to find this. It says to use it to find both of these things. So I think we're going to be able to find f of 2 now. If we know that L'Hopital's rule is supposed to work on this, then that means the bottom would have to be 0, right? So we got to kind of explain ourselves though. Since it is known that the limit as x approaches 2 of h of x can be evaluated using, so we got to do L'Hopital's rule, but kind of go backwards. So since we know it can be evaluated using L'Hopital's rule, also, by the way, this is another different spelling of his name, L'Hopital's rule, then the limit as x approaches 2 of the top, this is what you would usually write on a free response problem if you're going to use L'Hopital's rule. You'd say, well, the limit of the top equals the limit of the bottom, and they both equal 0. So we can use L'Hopital's rule, but we're going backwards. We're saying since we know we can use L'Hopital's rule, then this should equals this, should equal 0. And so from that, we're going to say, all right, well, 1 minus f of 2 cubed equals 0, which means that f of 2 cubed equals 1, which means that f of 2 equals 1. So that's a point. Now, this is worth 4 points, so we got a lot of points here. Now, we also need to find f prime of 2, okay? So since we can do L'Hopital's rule, we haven't done L'Hopital's rule yet, by the way, you would end up taking the derivative of the top and bottom, right? So we'd say, using L'Hopital's rule. So we know we can use it, but we haven't used it yet. We've used the criteria to use it to help us find something. But now let's go ahead and use L'Hopital's rule because that's going to bring in the derivatives. And since h of x is twice differentiable, then the limit as x approaches 2 of h of x, which equals the limit as x approaches 2 of x squared minus 4 over 1 minus parentheses f of x cubed, then it's going to directly equal the limit as x approaches 2 of the derivative of the top over the derivative of the bottom. Now, the derivative of the bottom, the derivative of the 1 is going to go away. So it's going to be 3 times f of x squared, but then you got to multiply by the derivative of what's inside, chain rule, and you get f prime of x, which is good because that's what we want. So then we're going to plug 2 into this, and we're going to get 4 over 3 times f of 2 squared times f prime of 2, which is what the other thing we're looking for. Now, we just found f of 2, right? On the last problem, it was a 1. So this is going to equal 4 over, okay, so I think I missed something here, and I made this mistake earlier. So there's a negative here, and I just lost it. So this is going to be negative 3 f prime of 2, okay? Now, since h is twice differentiable, that means that h is continuous, right? By the definition of continuity, the limit as you approach h at x equals 2 should equal the value at h equals 2 by the definition of continuity. And we know that it's continuous because earlier they told us that h is a twice differentiable function, which means the second derivative exists everywhere, which means the first derivative is continuous and smooth. And that means the first derivative exists everywhere, and the original function is continuous and smooth. So that means that 4 over negative 3 f prime of 2 should equal h of 2, which they gave you at the very beginning of the problem was 4, which means that negative 3 f prime of 2 equals 1, which means that f prime of 2 equals negative 1/3. So that's another point. And then the fact that you set these equal to each other, definition of continuity, that was a point. So that was definitely a tough problem. Now on to the last part, part D. Part D is tough also. And I'm running out of room here, and part D is kind of a funky one. But part D is only worth 1 point, so don't freak out. If you're running out of time, who cares? The bulk of the points are part C and D. So part D says, it is known that gx is less than hx for less than or equal to hx for 1 to 3. So I'm going to write that down. Gx is less than or equal to hx for 1, 2, 3. And then they say, let k be a function satisfying this other inequality relationship. They're saying there's a new function k, and it's between g of x and h of x, I guess, for 1 to 3. And it says, is k continuous at x equals 2? Justify your answer. Now, to justify continuous, you probably need to do like definition of continuity. But let's see what happens here. So I just wrote all that information down. Now, here's the deal. The fact that this is between these two functions, okay, and at x equals 2, we know their values, right? They told us that g of 2 equals h of 2 equals 4 at the very beginning of the problem. So this is kind of like that sandwich theorem. They call it the squeeze theorem, but we talked about it. We called it the sandwich theorem. That's where two functions end up being right between, or a function ends up being right between another two functions. And so then you can actually find the limit of it, because the only possibility is if k is between g and x, and at x equals 2, they're both 4, then k has to be 4, right? I mean, that's the idea, right? But writing it down on for response is a little more. So we're going to say, since g of x and h of x are differentiable, and therefore continuous themselves, right? Remember, they told us that they were differentiable, twice differentiable. So the limit as x approaches 2 of g of x equals g2, which equals 4. And the limit as x approaches 2 of hx is going to equal h2, which equals 4. So this is the definition of continuity, that the limit agrees with the actual value of the function. Otherwise, you can have a hole or a jump, but still have a limit, but not be continuous, okay? And since g of x is less than or equal to k of x, which is less than or equal to h of x, on 1, 2, 3, by the squeeze theorem, or you could probably say sandwich theorem, by the squeeze theorem, the limit as x approaches 2 of k of x is going to equal what they both equal. They both equal 4. Now, we haven't proved it's continuous yet, but we've proven what the limit is. Okay, if you're going to prove that something's continuous, you got to show what the limit is, both sides limit, and then you got to show the value and show that they agree. And g of 2 equals 4, which is less than or equal to k of 2, which is less than or equal to h of 2, which equals 4. Then k of 2 equals 4. So we first are showing that the limit of k as we approach 2 is the same as the limit of h and g, since they're differentiable and continuous, and we know their value. So what we've done is we've proven that the value of k equals the limit as x approaches 2 of k of x, right? And that's the definition of continuity. So k is continuous at x equals 2 by the definition of continuity. Anyways, it's kind of a funky problem, but it was worth 1 point total. So don't spend all your time on it. Don't get all like stressed out about it. Okay? Something weird, something hard, they're usually not going to make worth a ton of points. Okay? Make sure you get all the ones done that seem like they involve basic calculus work that we do all the time. Okay? Anyways, that's it. Really good practice for this year's AP test.